Hi, everyone. Today we are going to work on some probability problems, specifically how to make predictions. This aligns with IXL assignment 3.8c. So remember, when we're working with probability, there are two different types, both experimental and theoretical. Let's first review the experimental probability. That happens when you actually perform an experiment. So in this example we see here, somebody rolled a die 1,000 times, and out of that 1,000 times that they rolled the die, the number 5 appeared 140 times. So therefore, the probability of rolling a 5 is 140 out of 1,000. When we have theoretical probability, that's when you are theorizing. It's what you expect to happen. So in this case, we're like, all right, we have a die and there are 6 different sides. 5 only appears on one side. Therefore, the theoretical probability of you rolling a 5 would be 1/6. You have a 1 out of 6 chances of rolling a 5. When we are working with making predictions, one of the things that is needed is taking the probability that we're given and setting up a proportion. So let's quickly review proportions, and then we'll put both of these concepts together in a moment. So remember, when you have a proportion, that's when we have two different ratios, typically written in fraction form, and they are equal to each other. So in this case, we have 3/12 is equal to 19 over x. The way that you solve proportions is through cross multiplication. So we have 3 times x, and we can set that equal to 12 times 19. And then we would go forward with that and solve our problem. So first we would start with 12 times 19, which is 228. So we have 3x is equal to 228. Now we have a one-step equation, which means we can divide both sides by 3 to find our value of x, which would be 76. The method that I just showed you is the way that I use all the time because it doesn't require any guessing or anything like that. It's an exact method. We can follow those exact steps and get the correct answer each time. The way that this image shows you is kind of using that guess and check method, and it's another option, but as we can see here, they got the same answer. They found that in order for this to be a true statement, in order for these two fractions, two ratios, to really be proportional, to really be equal, that x has to have a value of 76. All right, let's hop on over to IXL so we can combine these two concepts and make our predictions given our probability statements. As you can see, we have now moved on over to IXL. Remember, the code is 3.8c. And then, as always, I want to quickly remind you that IXL has some great things to help you out. So you can click here to learn with an example. It'll walk you through step by step. Or you can click on this to watch a video to see somebody else explain it, because sometimes it's nice to get it from a different point of view, a different voice. All right, let's look at our first question here. A florist sold 16 flower bouquets yesterday, including 8 lily bouquets. Based on the past data, how many of the next 10 bouquets sold should you expect to be lily bouquets? Before we even answer this, this is a perfect one to explain why probability and why making predictions can be helpful in the real world. If you are the owner of this business, especially if you think about flowers, they only have a limited lifespan. So if you track your data, you see how many different types of flowers, how many different types of bouquets are being sold, it will help you make predictions so you can make a good order and not, potentially order a bunch of flowers that aren't going to sell, and then you end up losing money when they die. All right, so back to the question, now that we've made that connection, we first want to set up our experimental probability, which would be this first sentence right here. This is the information that we know. The florist sold 16 flower bouquets, and out of that 16, because it says including, 8 of them were lily bouquets. So we have 8 lily bouquets out of 16 total that were sold. Whenever I make my first fraction here, my first probability fraction, I always want to simplify, because the smaller your numbers are, the easier it'll make it in the future. So 8/16, we can divide that by 8 to simplify, giving us a 1/2. Now, we want to use this to make a prediction to know of the next 10 bouquets do you sell, how many of those would be lilies? So we're going to use this to set up our second ratio, our second fraction. Since we're making a prediction, we can assume that they're equal, set up our proportion. The trick is to make sure that your labels match. So if we look at the top here, or our first one here, the numerator is representing the number of lily bouquets. Well, that's what we're trying to figure out. We don't know. So whenever we have an unknown value that's represented with the variable, I'll just go ahead and choose the letter X, because L for lily would look like the number 1, and I don't want to confuse myself. But then this time it's out of 10 bouquets, which makes sense because the denominator here is our total, so out of 10. So we have our proportion set up, 1/2 equals X over 10. And we can use cross multiplication to solve this. So first we'll multiply 1 times 10, which is simply 10. And then next we'll multiply 2 times X, which is 2X. If we solve this equation for X, the inverse of multiplication is division. So we're going to divide both sides by 2, giving us the answer of 5, meaning we can expect that of the next 10 bouquets sold, 5 of them will be lily bouquets. All right, let's try this question. You select a marble without looking and then put it back. If you do this 90 times, what is the best prediction for the number of times that you will pick a green marble? Initially, when I look at this, my brain's like, wait, there's not enough information for me to solve this. But there is. This is one where we're making a prediction based on the theoretical probability, because it didn't give us the experiment. We haven't performed the experiment yet. We're going to, and we want to make a prediction on what's going to happen. So the important thing here is it tells us that after we select a marble, we put it back. So that means I am always pulling from these 3 marbles that are shown here. If we want to know what the probability is of picking a green marble, what would be the theoretical probability of that? Well, that would be 1/3, because there is 1 green marble and there are 3 total marbles. So 1/3 is our theoretical probability. Now, to make our predictions, we are saying, all right, if we were to do this experiment 90 times, how many of that 90 would result in a green marble? Well, 90 times is the total number of times that we would be pulling that marble. It's going to go in our denominator. Oops, my question changed, but that's okay. I'll just scroll down a little bit and we'll keep solving. Sorry about that, guys. And we don't know how many times we're going to get a green marble. So that will be an X right here. Now we can use cross multiplication to solve, which means we'd have 3x equals 90. And then if we divide both sides by 3 to solve for x, x is equal to 30. Meaning that if we were to continue and do this experiment 90 times, 30 of which would result in a green marble. All right, let's go ahead and try this one that IXL switched to. Since you guys already saw the question, might as well answer it. If you roll a 6-sided die 36 times, what is the best prediction possible for the number of times you will roll an even number? Ooh, interesting. So first, we see here that this one's similar to the last problem where we, aren't given an experiment that's already been performed. We're going to take the theoretical probability and use that to predict. And we're wanting to predict an even number. And if it's a regular 6-sided die, how many of the numbers on that die are even numbers? 3 of them are even, because 2, 4, and 6 are all even numbers. So we have 3 even numbers over 6 total sides. If we simplify that fraction, we get 1/2. And then we want to know, if we perform this experiment 36 times, what is, the best possible prediction? I'm actually going to show you guys a different way of doing this. So on the last example, the one with marbles, we set up a proportion and we solved the problem. That's one method. With problems like this special little niche here, where you're taking the theoretical probability and then just performing that experiment X amount of times. So last time it was 90 times. This time we're performing the experiment 36 times. We can honestly simply just multiply the probability by how many times we're performing the experiment and get the answer that way. It ends up working out the same as if you were to go ahead and set up a second fraction like we did on the last example and cross multiply. So here, if we take 1/2 times 36, that would be 36 over 2, and 36 divided by 2 is 18. So that means we can predict that we would roll an even number 18 times. All right, let's do a couple more problems. So Jackson's mother recorded what color shirt Jackson wore on each day recently. Considering this data, how many times would you expect Jackson to wear a black shirt in the next 42 days? All right, this one is very similar to the first question that we did, because we have experimental data that we're taking and making a prediction off of that. So we specifically want to know how many times he wore a black shirt. Well, we can see that he wore a black shirt 6 times. But what were the total number of days that his mom recorded the data for? It doesn't just straight up tell us. We need to add all of these numbers in our table here, because those are all the different days she recorded data. So 8 plus 10 plus 11 plus 1 plus 6 gives us 36 total days. And then if we simplify that fraction, we can simplify by dividing by 6. We get an experimental probability of 1/6. Now, in this case, we do need to set up our proportion in order to solve. So we do not know how many times he wore a black shirt, but we know that it occurs over the next 42 days, meaning we can cross multiply and solve. 1 times 42 is simply 42. And then 6 times x is 6x. Divide that, and we get the answer of 7. So we can predict that over the next 42 days, Jackson will wear a black shirt 7 different times. All right, let's go to our highest SMART score value here and answer one final question. In this case, just glancing at it, it looks like the main thing that it's increasing in difficulty is that we're having larger numbers that we're dealing with. But that's okay, we can do that. So of the last 320 flights to arrive in Newton Airport, 8 were late. Considering this data, how many of the next 840 flights would you expect to arrive late? So this is another one where we have an experiment that's been performed, or we've collected, that data. And I can see here that there were a total of 320 flights. 8 of those 320 were late. And the reason I always specify that, or I have been on the past 2 that are like this, is it's good to know that we don't need that the 8 is included in the 320. I don't need to add the values up like we had to in that last example with shirts. So always read it carefully to make sure that that value is included in your total and you don't need to do any, additional steps of addition. All right, I know that I can simplify this because even though I don't really know my factors of 320, that's an even number and 8 is an even number. So I can at least simplify and divide by 2, which would give us 4 over 160. And I could have picked something larger because they're both even numbers again. So let's simplify, let's divide by 2 again, giving us 2 over 80. Oh, definitely could have done something larger. So let's divide by 2 again, and we get 1 over 40. Now that I've seen what it simplifies to be, when I look back at this original problem, yeah, it says 320. Look at that 32. I know 8 goes into 32, so I should have just tried 8 from the beginning, or 4 even, if I had thought about it. But I didn't, so that's okay. It happens. That's the beauty. You can just keep simplifying until you get the simplest fraction, which would be 1/40. But I am going to rewrite that since I've ran out of room. Now we need to create our second fraction here to set up our proportion. And we are taking 840 flights. And we want to, once again, predict how many we can expect to arrive late. So that'll be in there, our numerator. We'll do cross multiplication, which means we have 40x equals 840. When I divide both sides by 40, we get, 21. So we can predict, we can expect that 21 of those flights would end up running late. All right, it is now your guys' turn to try it. If you want to see a few more examples, remember to check out that video that IXL has for you, or when you get to that first problem, click Learn with an example. All right, good luck. If you need anything, make sure to reach out. Bye, guys.